Let's do an example problem to help you work through assignment 8, where you'll be assessing the solar resource and comparing it to various energy needs. Remember that the solar constant, which is the amount of energy coming from sunlight at the top of the atmosphere arriving at the Earth, is 1,360 watts per square meter. That's 1,360 joules per second per square meter. So there's a rate per time and also per surface area. But if we take the curvature of the Earth, the spherical shape of the Earth, and day and night, and the atmosphere, which absorbs some sunlight before it gets to the surface of the Earth, then the average solar flux at the surface, including day, night, and all that stuff, is about 240 watts per square meter. So that's because the cross-sectional area of the Earth is pi r squared, but the surface area of the Earth is 4 pi r squared, so it's 4 times bigger. So at any given place on the Earth, I've only got about a quarter of that 1360, and then before I even get the 1360 into the Earth, I lose 25 to 30% of that to the atmosphere. So that's how that 1360 becomes 240 watts per square meter. So our example problem, let's say how many or how much area of solar panels needed to supply electricity for Josh's house. And we're going to assume that I've got some storage capability or something like that. So I'm not going to worry. I'm going to average this out over the whole year, and I'm not going to worry about whether or not I've got batteries or something like that to take care of things. So the first thing you need to do is know how much energy is that. So the energy used, electrical energy used by my house is about 14,000 kilowatt hours per year. And the other piece of information we need to know is we're going to need to know the efficiency of the solar panels. So let's assume solar PV panels have an efficiency of 20%, which is very close to what the efficiency of the panels that are actually on my house are. And now I know the total amount of energy I need to produce in a year. I've got this 240 watts per square meter. I've got to reduce that by this 20% efficiency. That'll tell me how many square meters I need in order to get that much energy. Well, what I'm going to do is I'm going to take that energy, E equals 14,000 kilowatt hours, and I'm going to convert it to what's the power of that. That is in 1 year. So the number of hours in a year is 24 times 365, and that number is 8,760 hours. So that's a time. That's the time in a year. Remember that power is energy over time, so the power that this system needs to provide is 14,000 kilowatt hours divided by 8,760 hours, and that is 1.6 kilowatts. 14,000 kilowatt hours divided by 8,760 hours gives me a power, an average power that I need to be producing this of 1.6 kilowatts. And next then what I want to do is say, okay, how much area do I need of solar panels to get 1.6 kilowatts? Well, the power from the sun is 240 watts per square meter. So the power of my solar PV system is going to be power from the sun times the area of the PV array times that efficiency of 20%, which is 0.2. So I want that to equal my 1.6 kilowatts. So I have 240 watts per square meter times the area in square meters times 0.2 has got to equal 1.6 kilowatts. Okay, that's my average solar energy averaged over the course of the day in watts per square meter. I multiply it by the area, the number of square meters, that'll give me the total number of watts hitting my solar PV system, and then the 0.2 will account for the fact that only 20% of that 240 watts per square meter is converted into electricity. And all of that needs to add up to be 1.6 kilowatts. And the thing I'm looking for is the area of that solar PV system. So I can just rearrange this equation. 1.6 kilowatts divided by 0.2 and divided by 240 watts per square meter. So the square meters come up in the numerator. I divide by watts per square meter. That's meter squared per watt. I've got kilowatts in the numerator, watts in the denominator. So let's handle that unit conversion. That's 1,600 watts divided by 0.2 and 240 watts in meters squared, and the watts cancel. And then I have my answer, which is 1,600 divided by 0.2 divided by 240, and I get 33.3 square meters. So that's the area in this exercise, this example, that I would need to cover with solar photovoltaic panels with 20% efficiency to averaged over the course of the year, provide enough energy, electrical energy, to supply my house with its annual use of electricity. So I actually have a system, and it doesn't quite meet my house's annual electricity needs, but almost, and it is bigger than this, and the reason that it's not quite meeting it is because the 240 is a little bit high for where we are here in Central Florida because of cloudiness in the summertime, and also because the solar panels on my house are mounted straight on the roof, and that means that they're not pointed optimally for the sun. It would be, I would get more energy from them if they were on a flat surface, or even better if they were pointed towards the south. But ballpark, that's pretty close to what I've got. And so that shows you how you would do these sorts of calculations. You need to take into account the fact that you're dealing with a rate of energy per time, but also a rate of energy per area when you're doing calculations with calculating the solar resource.